Hello, welcome everyone. My name is Juan Pe. I work for Ableton, which is a Berlin-based music software company. And at Ableton, we made an implementation in C++ of transducers that I would like to show here. But before I start, I would like to thank everyone for being here in this room in spite of all the spam that we got about the static analysis session. But I have two good news for you. The first one is that we're going to talk about functional programming, which, to paraphrase Sean Parent, in a way tries to eliminate incidental code structures. So hopefully, by leveraging the tools presented today, we can reason better about the correctness of our code and don't need to resort to proprietary static analysis tools. Second good news is that everything that's presented here today is based on an implementation and that we made that is open source, so you're really welcome and encouraged to study the code, to modify, to improve it, and to share it with others. So let's get started and first talk about what is a transducer, which is a funny word that, I don't know, causes a little bit of what the fuck situation when you say, oh, what are you going to talk about in this conference about transducers? And then people go and look it up on the internet, and they get definitions like this in Wikipedia that says like a transducer is a device that converts one form of energy to another. Like, I don't know, is this going to convert my chakras or clean up my karma? And if you look for pictures, then you get pictures of devices that I have no clue what they are for. I'm probably sure that maybe there are some electrical engineers here that know, not me. So what is this, right? What is a transducer in the context of programming? And in the context of programming, the first person that I know of that used this term is Rich Hickey, who is the main author or original author of Clojure, the programming language, which is a Lisp-based or a Lisp derivative that runs on the JVM, on the Java Virtual Machine. And he introduced transducers in the latest version of the language, which came in, I think, March or May this year. And he did so when researching how to unify the way he operated or he described transformations on collections and the way he described transformations on channels. We will come back to this later. Then last summer, when we first saw the blog post from Rich Hickey about Ableton, we were very impressed about the possibilities of this, and we were working at Ableton in a research project where one of the topics that we were working on was trying to be able to describe the data model of an application, in this case music applications, in a way that is declarative, that leverages the reactive functional programming paradigms and so forth. This project is not going on anymore, but a lot of the code that we developed is now under this library called Atria. The URL is here, it will come back later, and it will be shared with the slides at the end. So what is a transducer? One of the most simple transducers that we can implement is this. And if we want to define a transducer, we could say that a transducer is a transformation over a sequential process. We will come back later to the sequential process part, but what we can see here is that we have a call to something called map, and we pass to this a lambda that describes a mapping between integers and strings, right? And this represents something very similar to the map function that you have in languages like Python, Clojure, Haskell, and whatnot. In C++, you will call it transform, but there are some differences in the parameters you see and so forth. But the important thing to get here is that it's a transformation. But it's a transformation that is also a value, and this is not obvious or immediate in C++, because in C++ not everything is a value. But transducers are a value. So the transformation that is described by the result of this map thing can be stored in a variable and can be copied around. It's actually it can be a regular value, can be passed around, and so forth. It's a value that is also composable. So you can use this transformation that you have here as a value and take other transformations that are described in other parts of the program and compose them together to make a more complex transformation. In this case, we compose the mapping that we showed before with a filtering of the integers that will let pass only the integers that are greater than 0. And we compose them with the comp function here. This comp function, actually, the name comes from Clojure, and it's nothing more than function composition. So this also tells us that a transducer is just a function. So another important thing, and probably the most important thing about transducers, is that they are transformations that are independent of the source and independent of the process that is putting the values inside the transformation. As some of you may have noticed, unlike in the calls to transform, filter, and so on of the STL, here there is no sequence parameter. And this is so because the transducers, they don't have information of what they are transforming. That comes later in another part of the program. And actually, these transformations can be multiple. So one way to apply it to a concrete transformation would be this. Our library provides, for example, this sequence function. The sequence function takes a transducer, in this case the XF that we have here, and it takes a second parameter which will be a range. In this case, it could be a vector of ints that we can deduce from the signatures here, that is the input of the transformation. Now, what this returns is another range that acts as an adapter that applies the transformation on the iterators lazily. Basically, every time you run through the iterator, you are applying the transformation, and you can use it with standard STL algorithms now. So you could, for example, copy the resulting strings of applying this transformation into another container, for example. Yes?
Can the transducers use the VARIADIC lambdas?
Yes, they can. We will come back to that later. Another way to apply the transducer, for example, if you wanted to, I don't know, use the standard input and output, you can compose it with these two other transducers, read that whenever it gets a pulse, and we will come back to this notion of pulse later, reads from the standard input, in this case integers, and this other one that just writes to the standard output. And this run will basically execute the transducer until there is nothing else to be done. And as we can see here, in a very different context, we're also using the transducer to, in this case, transform output coming from and to files. But the most interesting use case of transducers is that you cannot apply it only to data that you have already available and that you can pull, which is what you normally do with iterators, right? That's a pull model. You can also apply it to push models. So probably many of you already have used boost signals. How many of you have used it already? Okay, great. So as you know, boost signals is like a general implementation of the observer pattern, of the delegate pattern. So you have this boost signal here that has a signature. In this case, it's a signal that takes ints. And the idea is that you can connect to it and later emit it. And you can have many observers, many functions that are observing on it and kind of respond to this integer. It's very useful to model, for example, UI events, like, for example, mouse clicks, right? So you could have a function like this. Actually, I have in one of the examples, this is not provided in the library because I didn't want to depend on boost signal, but one of the examples actually provide how to write such a make signal function where you take a boost signal and a transducer, and what you get here is another boost signal that in this case will have the signature void std string because this transformation outputs std strings. So now we can connect to this second signal, and when we emit the first signal, the second signal, first it might get emitted yes or no, or even more times, depending on what the transformation we have. In this case, because we're filtering integers greater than 0, when we pass 41, it actually passes the 41 on, which gets converted to a string, and the string gets passed to the listeners. When we pass a -10 to the first signal, it will actually not call the second signal, right? So you can see maybe with this code already how it's useful. It can be useful to have this transformation expressed in a way that you can use in all these various contexts. And it's very important to what I already said about sequential processes, which is this word that we use that transducers transform sequential processes are not just ranges. Even though in many of the examples that we will show through the code, because it's very easy to express ranges in C++, we will use ranges. You can do it to many kind of processes. These processes can be ranges, as we already saw, right? But one very useful example, and that's why we wanted to do like declarative reactive programming with this library, is, for example, GUI events, right? So when you click the mouse is a source of input. That is one single source of input. And when you click it, you get an event. Then you click it again, you get another event. So there is a sequence here. It's a sequence that happens in time. The abstraction of the transducer, because it's kind of a push model, actually allows us to transform this sequence. CSP channels, so this is concurrent sequential processes. The language Clojure and many languages now, also like Go or Rust, include this notion of inter-process communication that doesn't use mutable state. So you have these channels when one process pushes data and the other process pulls data from it. If you wanted to be able to connect processes with different interfaces, you can use a transducer in the middle to kind of adapt the kind of channel that one is expecting to the one that the other one is expecting. Network sockets could be another example of something that is a sequence, right? So once you have a socket, you have a stream of data that is also following a push model because the data comes from the internet as the other computer is sending it. And you could also transform it with a transducer. These are just examples, actually. You can probably think of your own. So one metaphor that I like to use to think about transducers is machines in an industrial processing line, like this one, right? So here we have a machine that takes as inputs these kind of pasta slices and this creepy red sauce, and it just folds them together to produce something that is maybe like a cannelloni or whatever. This machine here, which is, if you're familiar already with functional programming, is something like a zipping thing that it's doing. It doesn't care about where the pasta and the sauce come from, right? They could come from different places. It just takes it as they come and then produces the cannelloni and moves it forward, right? It doesn't return a value, which is different to how we think normally about doing a transformation in C++. You return something. Here in a transducer, you call the next one. You pass it over, right? You have some outputs that way. A movie that I really like is Modern Times, which is this critique on current or on the Industrial Revolution and the dehumanizing effects of the Industrial Revolutions, which gives us lots of GIFs that are useful to describe transducers. In this case, we have this transducer here that takes plates of food. So it could be like a vector or an array of pieces of food. And this is very similar to a cat reducer that takes a collection and then passes the individual pieces of the collection along to the next transformation in the transducer, which in this case is Charlie Chaplin. It could be a human transducer that transforms food into poop. So this human transducer then can be combined with different transformations, right? It doesn't have to be combined always with this cutting thing. It can be combined with a soup dispenser, but we have to be careful. We are talking about C++. Compiler errors can be harmful. Okay. So now we know, I think, enough about what's the concept behind the transducer. It's time to talk about how does this work? How does the transducer do all this magic? So to try to deduce kind of the concept of transducer, Rich Hickey, the inventor of it, uses this sentence, which I really like, which is that a transducer tries to extract the essence of map and filter. And by looking at map and filter, at the traditional implementations in a functional language of map and filter, you can look at the commonalities and try to, from it, extract the essence of a transducer. Let's do this derivation process because we're in a C++ conference. In C++, it actually works the same way that Rich Hickey does it for Clojure. Here we have a very simple implementation of the transform function, which is the equivalent for map in functional languages in the STL. And transform function takes two input iterators that describe a range, which is something that we want to transform, that's our inputs, and produces into this output iterator a sequence which is the same as this one, but transformed with the values transformed through this mapping. And the mapping here is fn, right? The way this works is, well, it's very trivial, right? We just loop over it, and then we apply the function to every element and store it in the iterator and increment the iterator. At the end, we return the final state of the iterator. If we look at filter, it's very similar. The signature, instead of a mapping, what it takes is a predicate. Should the element be in the collection or should it not? And what it does is actually very similar, but instead of projecting the values of the collection with the mapping, what it simply does is to say, should I put the element or not with the predicate? We can see commonalities here, right? The blue parts, or this shell, or this loop is the same in the two functions. So we could think about how can we extract this. There is another part that is common, which is the way they are doing the output, right? So there is something essential to the mapping and the filtering that is happening that is not definitely outputting things into another collection. And it is neither iterating over a collection. Let's get rid of the blue part first with accumulate. Accumulate is a function of the standard library that is in the header numeric. And a bit sad that it's in the header numeric because it's, in a way, the most generic algorithm you have in the standard library. And it's in this header where it looks like you can use it only for, I don't know, summing things, which is what the typical example in which you use it. But actually, this function is basically more general than map and filter. It's the most general way to iterate sequentially over a collection, right? Because the signature of this function, what it takes is, again, two iterators, the sequence over which we want to iterate, but then what we do over the sequence is totally abstracted. There is a state that is often called accumulator as well. I might use the two words interchangeably, which is, well, the state of the computation that we're doing over the sequence. And then there is this this fourth parameter here, which is the reducing function. Reducing function comes from the fact that this function in Clojure is called reduce, in Haskell is called fold. And we call this the reducing function. Oftentimes I will call it just a step because it's simpler. And this is what we do inside of the loop. And inside of the loop, the only thing we do is to say, well, a step function, I give you the input, I give you your current state, you give me the next state, right? It's a very functional way of thinking about transforming the collection. In C++, normally you don't deal with state in this way. You have local variables for that, mutable local variables. But here, the step function can actually perform a computation with mutable state in an abstract sense without mutable state in a concrete sense, because it just takes a state as an argument and returns it a new value, which is going to be the next state. The other part, the red part, we can also abstract. And we can abstract as a reducing function for accumulate. This reducing function here will allow us to output something into an iterator. What's the state? Well, the state is the current position in the output iterator. It's gonna take one, increment it, and return another one. And then what it does with the input is to copy it in the current position in the output iterator. If we combine these two functions, if I simply pass here the step function, what do I get? I get copy, right? I get the equivalent of std copy. So we can as well wrap instead this output ref into two simple lambdas to get transform and filter, as we see here. So transform, we'll just call the output, the step function for the transform implementation, we'll just call the output step function. It passes the current state. It actually doesn't even need to know this thing what the current state is. It's actually an output iterator, but this thing doesn't know. The output doesn't. The output step does know. But what this does know is that it needs to map the inputs through the mapping. The filter is simple. It's similar. Sorry, it's simple as well. Why not? It just in every step, what it does is to look with the predicate at the input. If the input passes the predicate, then it passes it along to the output step function. If it doesn't pass the predicate, well, it still needs to return something. It returns the current state, which will have the effect of not incrementing the output iterator and so on, right? What is what defined? Sorry, it was defined in the previous slide. So it's this one here, right? This lambda here that takes an output iterator, the input, and just outputs and increments. So the last thing that we have hard-coded here is, this output RF here. This is not essential to map and filter. So how do we abstract this? We can abstract it like this. So this will be, finally, our implementation of the map transducer. The map transducer, we could use it actually to do exactly the same that we will do with transform, but just using the building blocks that we built in the previous slides, like this. How does this work? Because, I mean, it's like 3 levels of lambdas. This is not typical C++ code. Let's look at what happens step by step. So the outermost point of this expression here is this call to map, right? And this call to map, what it's doing simply is capturing the mapping function. So this fn was the mapping function that we were passing to transform. It just captures it somewhere in this variable. So we can use it later in the other lambdas. Now we come to the red part. This red part is what we will normally call transducer, actually. And this transducer, what it does simply is to capture a reducing function that we pass as a parameter, in this case, the output RF, the thing that actually outputs to iterators, and keeps it in the scope. What it does then is it returns another step function. This step function that it returns is what it's finally passed to accumulate to do its job. And inside this step function, it just adds something very similar to what we did in the previous slides, but using the parameters that we have available through these captures, right? So it calls the mapping over the current inputs, passing it to the next step function that when bound like this is going to be output RF, but it could be something else, right? That's how we get the independence of the process and the composition. And finally returns the state. For filter, it's exactly the same structure. We have in the outermost layer capturing the arguments, capturing the parameters. In this case, it's a function. It could be actually an integer, for example, if you're implementing something like take. It could be nothing, actually. Some transducers don't even have this layer. We will see some later. Then in the next layer, we bind it to another reducing function, and finally return another reducing function, which is the one that is going to do all the work with all the parameters that we captured along the way. So just to be clear, because I've used many terms here, what is what? The reducing function. What is a reducing function? Reducing function is what we pass to reduce, what we pass to accumulate. It's something that takes a state and some inputs as a parameter. In here, we see some, the reducing functions that we see are here, the parameter to the transducer, and the result of the transducer, right? And we are calling the one that is grabbed as a parameter inside the transducers. What's the transducer? The transducer is, again, a function that takes a reducing function as parameter and returns another one, and builds chains in this way. The state, also known as accumulator, is the first argument of the reducing functions. And the transducers normally don't make assumptions of what's in the state. It's simply something that pertains or is in the domain of the particular computation that we are doing in the most nested reducing function. Like for output, it was an iterator, it could be something else, right? And finally, we have some inputs, which is the arguments of the reducing function that the transducer builds. That's what I will call sometimes, these are the inputs of this transducer. This transducer takes this kind of inputs. That's because the reducing function that the transducer produces takes these inputs. And then what are the outputs of the transducer? The outputs of the transducers is not what the functions return. The outputs of the transducer is what the transducer passes to the next reducing function, right? That's what one could call the output of the transducer. So we decomposed all this. Now we can say, it smells like essence of map and filter, right? Smells so good. Lavender. So One thing to note here, though, is especially for the ones that are already used to functional programming, what happens when you compose transducers? As we saw in the introductory slides, and we can show it again here, if I wanted to make a function that filters and maps sequences, I could do so by simply composing the two transducers before passing the output at F. But here, if I want to filter before mapping, filter goes before map. That might be a bit unusual if you're used to, in Haskell, you will compose it the other way around. You compose on the right side the filter and then the map. But this is because the transducers, they don't directly transform the collection. The transducers, they are kind of factories for the actual reducing functions. Yeah, they are building these layers, and that's why the outermost layer has to be the first one. Yeah, so to see an example of this, again, we can expand the previous expression. So if we expand the composition, what we get is that we pass the output at F to the result of the map, and all this to the result of the filter. And to see how this layering works, it's like we can conceptually think of we're building a function, right? It's like we're writing code when we are composing transducers. In the innermost part of the function, we have the output at F. Now we pass it to the map, and we are like in the function going one line before and saying, well, now the inputs are actually the inputs mapped. This is actually pseudocode, right? Because the types wouldn't match and so forth. But you can imagine this, right? Like we are simply saying, okay, the inputs are mapped. And with the filtering, what we're doing is adding an if around it. So this is how the layering works. The transducers are kind of taking a step function and changing the code by basically grabbing it and grabbing it and grabbing it. It's like an onion. All right. So first thing before we continue also is to know that in Atria, in our library, we use the Clojure's nomenclature. I think this makes it a bit more easier to relate to a lot of what's written already about transducers in the internet. So we will not use the word accumulate anymore. We're going to use the word reduce. And the signatures change a little bit. So our reduce takes the step function first, then it takes the initial state, and then takes ranges. Not iterators separated, it takes ranges. Then there is this transduce function, and transduce is basically a very thin wrapper around reduce that takes a step function and the transformations separate. Then there are utility functions like, for example, into, that takes the transducer, some ranges, and copies into this collection, passed as first argument, the content of the ranges transformed with the transducer. There is into vector, which deduces the type of the resulting vector, because you should be using vectors most of the time in your life. And there is stuff like sequence, which does things lazily instead. Okay, so let's talk about some more advanced topics on how to use transducers. How our implementation works as well. The first thing to know is that transducers are variadic. And some of you might have already noticed, actually, that when I implemented map and filter, there were these ellipses next to the inputs, right? Because the inputs could be of any number. So actually, unlike in Clojure, because in Clojure the overload the arity of the reducing function for different purposes, we used a different design that allows us actually to have even transducers of arity 0, where the reducing function only takes a state, takes no input. And this is very nice if you have like some other source of input, you can use it to generate values. So if you wanted to generate an infinite sequence of random values, you could just do something like this, right? So the arity of this transducer, we have to talk, when we talk about the arity of the transducer, we have to talk about the inputs and the outputs, because the outputs can also be multiple, right? So this will be, it has like 0 inputs and multiple outputs. A 0 input is what I call a pulse. These pulse will be generated here by iterating over the sequence. Whenever you do the ++ iterator, you're kind of calling the transducer. This generates a pulse, which is a calling to the iterator that passes no arguments, but then in the transducer that passes no arguments, but then the transducer might generate stuff. Then we have transducers, which are what we saw already in the other slides, that take one argument. So map, in this case, we have one collection, and we transduce it with a plus operation and this transducer, which just multiplies everything by 2. The result is going to be here the sum of all these elements multiplied by 2. The nice thing here is that, unlike if you used STL transform or something, this is going to be applied on the fly as we compute the sum, right? There is no internal value that you need to compute for the whole vector. But there are also transducers that take multiple arguments. And our operations over collections are like this. If you make operations over boost signals, you could also have ways to transform multiple boost signals or whatever. And here we have 2 vectors of different lengths, and into vector can, for example, transform the 2 collections, zipping every pair of elements with the operation plus. So it will generate another vector that contains 4.3 as first element, 4.2 as second element, 4.1 as third element, and then it wouldn't contain any more elements because there are not more elements in the second collection. If we wanted to simply generate tuples, actually, we can pass the identity transducer. And into vector, when it gets multiple inputs in the last step of the transaction, will actually zip into a tuple. So the identity here is actually the normal identity function for functional programming languages. It's a function that takes an argument and returns the same argument. That's a transducer, right? You take a step function, you return the same step function. You did nothing to it, but you're within the contract. There are other transducers actually that even generate more inputs than they take. So for example, here we have this mapping that this mapping takes no input. It's again a generator, and it produces tuples with 3 random numbers. Now, unzip here, what it's going to do is to take the 3 elements of the tuple and pass them as 3 inputs to the next iterator. To the next transducer. The next transducer here is a filter, and as you can see, it already sees the 3 elements of the tuple as different arguments. And it can do something like say, well, they have to be in increasing order. And then here we use a different transducer, which is called interleave, which what it does is it takes the 3 things that come in parallel and puts them serial. So this might be something that you want to do. I don't know. Okay, but we can see here, this is a more complicated example to illustrate like how transducers actually can like take less arguments, produce more arguments, and then this one is actually going to take 3 arguments but produce 3 different outputs, right, in one single step. So it's very flexible in this regard. But now we get to, I think, one of my favorite topics, which is state. How to do state inside a transducer. We saw already actually the mapping with random actually has state, right? Has global state. That's not very nice already. But let's look at a more concrete example of how we would like to do this with enumerate. Enumerate, the name comes from the Python function. I also did a lot of Python in my previous life. And in this case, you can use it as a generator. So you can use it just to generate sequences of numbers. But if you use it over other inputs, you can use it simply to tag every element with the time at which they occur, or not the time, but the order in which they occur, right? So in this case, we will get A 0, B is 1, C is 2, and whatnot. It can be very useful, for example, actually to create like a reverse map or something like that. How will you implement enumerate? The Clojure way actually of doing this, if you look at the Clojure implementations, will be something that to C++ I will translate it like this. Enumerate in the transducer, the first thing that we see is that it has no arguments, right? There is no parameter, so we can get rid of the outermost layer. We are directly in the transducer with the step function and the other step function. And what it does simply is, in the captures of the lambda, it defines a variable, which is going to be the counter. It's using C++14 things. Another disclaimer, we use C++14 in the slides, but the actual implementation uses C++11. The second disclaimer is that there is no move in any of the slides, even though you could add some. But I think that move semantics, they just make the code look very ugly on the slides. So it's an exercise to add the proper forwarding and whatnot here. So we have the counter here, and then simply on every step, as first input, we pass the current counter and increment the counter, so the next time you call the reducing function, you get the next value, right? What's wrong with this? I'm gonna let some cute animals explain it to you, right? There is hidden state here, it makes us very sad. Hidden state, mutable lambdas kill this cat mommy. And in the Ableton office, some people can get really angry about this, you know. You don't hide state, right? This might be a bit counterintuitive for a C++ developer, right? I mean, variables, states, that's what we always do. But here we're talking about a functional approach to doing transformation, and we already have a variable that represents a state as a value that we don't need to mutate, right? State goes here in this state thing here that we have. That's why we call it state, and we don't call it, I don't know, refrigerator. State doesn't go here, right? The nice thing is that if you really are able to abstract the state into the accumulator, then you can do even more powerful things with transducers. You could have transducers that go back in time because they keep the state from earlier executions, right? Like the possibilities are more open also with regards to parallelizing the execution and whatnot. So we would like to get rid of this state. What's the solution? The solution that we offer in the library is this state wrapper type. We need a state wrapper because, as I said, we cannot really make assumptions about the state that we get for the next reducing function, right? The state that we get originally is something that only the next reducing function understands. We don't do anything about it. So the only thing we can do with it is to attach data to it, to put data next to it. So we can use something that is a little bit like a tuple. In this case, we have our own type because we want to support type erosion and other operations and whatnot. This is basically a tuple that contains the original state and some data that we add to it, right? So our transducer, what it's going to do is to, get the state, grab it into more and more of these Russian dolls, and whenever you grab it, you add inside the box your little note with the information that you need for the next execution. The next time you receive it, you open it, you get your information, you pass it along. The tag thing, we're gonna talk about it later. It's basically to identify that this is your state, that this is your type, and then you can customize some behaviors. Let's look at this new implementation of enumerate. Let's see what happens with the state here. So if we have like a pulse, because we're executing it with no inputs, and we compose enumerate with this other kind of generic state, generic reducing function that we call here step. When we call enumerate for the first time, we get some state that we don't know anything about. It's just a symbol here. We get some state. And now what enumerate is going to try to do is to get its data. And for that, our library provides this state data function. Now, the state might contain already our data or not. If it doesn't contain our data already, we need to provide a way to retrieve an initial value. And this is done with this. We just return the current, the initial count, which is fixed to 0. So in this case, because it's the first execution, there was nothing here with data. This is just going to return the 0. Then we also need to unwrap it, because this is a state grabber thingy. Step doesn't understand state grabbers. It understands something else. So we need to unwrap it. Finally, we can call the next step function with the unwrapped state. We also pass, in this case, the 0, because that's the input that we're generating. And then when it returns, step did something with the inputs, but now it's giving us back some state of its own type, which is this rhombus here. What we need to do now is to grab it. We use the state grab function, and in this case, we need to put the next element that we want to emit, so n+1, right? So we just put it in this box. This is a representation for the state grabber containing the state that the step needs and our state. Finally, we return this, right? The next time we execute the enumerate, again, this is called, we unwrap everything. But now when we unwrap it, what happens? We already have a box. So this function doesn't get called. Instead, we get the data that we already have in there. We get the data, and that's going to be the input that we pass along. We also get some state that step returned. We pass it along. It returns. We grab it with the next count, which will be the 2, and so forth, right? So in this way, you could also imagine actually that this step, if it was another enumerate, it could also be returning a state grabbers and whatnot, actually. We don't care, right? At this level, this composes through the fact that we actually don't know, we make no assumptions about what that is. Yes? Yeah.
Just question, just wondering why there's a lambda with no arguments there to initialize the state instead of just passing a value there. Can that lambda have arguments in some cases?
No, the reason is because if you wanted to pass or to return like a fat value or something that you need to do some computation there, it's better if it's grabbed in a lambda. Like let's say you want to return a vector. I do it in other places. If it's a lambda, it's not even going to try to construct it or anything. Or a random number, yeah. Yeah, so it's a bit more flexible this way, but this is never going to take arguments because it's an initialization. All the arguments that it can use come from the other layers, right? Yes?
So internally, this is some optional or something, but the value is there or it's not there? Or?
No, it's actually, there is not an optional. It's actually the state, and we come to the next slide. The state changes on the first iteration. So this implementation of reduce, which I changed the layout a little bit to make it simpler for the changes I'm going to do with it, but it's very similar to the accumulate we had, right? So we have a first and last thing of some input range. We iterate over it, calling the step function. Now, what's the problem? The first execution of this loop, because I'm not using an optional or anything, the first execution, the type of this is the rhombus type. But this is going to return a state grabber. So I can definitely not assign it to this variable. So this is not going to work. The only thing we can make this work is by extracting the first iteration of the loop out. In this way, we can say in the first iteration, we call the step function. This is going to change the type. We assign this, and this is going to be the type that is already fixed for the whole reduction. Then at the very end, we need to unwrap all the layers and potentially even, like, I don't know, do more stuff that the state, there are some partial results in the state or whatever, so we need to complete the state. This complete state is going to return something of the original type and unwrap this. So this is the change we need to do here. Nonetheless, we are not done. We created a problem. We created a problem for filter, which I represent here with this transducer that lets pass some chocolate, but some chocolate it's for itself. Let's see what's the problem with filter. Filter now takes, again, a state and some input. The input here is a heart. then runs a predicate on the input. Its state is unwrapped, but it's composed with enumerate. This means that enumerate, if the predicate passes, wants to return something wrapped like this, right? But if the predicate doesn't pass, we're not going to get something wrapped from enumerate with a state. So, I mean, we could try to make up some data here, use abuse optional, as you said, but we don't know how to make this value. The only one that knows how to make this value is enumerate, and we don't want to call it because otherwise we will be generating an input that we don't want to generate. This is a problem. So we have a utility inside our library, which is call and skip. And in the change, you see now that we are calling the reducing function with this call wrapper here. This call thing, the only thing it's going to do is actually call a step with s and ins. Skip, what it's going to do is to not call it. Very simple. Now, what these two functions here allow us to do is that they do a little bit of magic. They detect that if you call the step function and if you don't call it, you will get a different type. Or you will get the same. If you will get the same, they do nothing. But if you will get a different type, then what they return is actually a union-like type, something like a boost variant, or an STD variant when we get it in the standard, or a C++ union. A union that can hold both the result of calling the step function and the result of not calling it. This way we can have the filter, and filter doesn't need anymore to invent a value of the next thing. It can just return what it has, and it's going to be wrapped in this thing, right? Call, another thing that it does is that when it gets the union-like value, it also unboxes it to pass the underlying value to the next reducing function. So that's actually, they do a little bit. We covered the problem of state. The next problem that we want to deal with is early termination. So some transducers need to terminate early. The example is take. So take says, I want to generate only 4 inputs, 4 outputs, sorry. And after 4 things, I want to finish. So we want this example to work, where I compose enumerate with this a generator with take, which says it's 4, and then pass it to into vector without any collection here, right? And it should be able to finish at some point. Same thing here. We actually have a collection here, but still we want to finish before we are done with the other collection, right? We want to finish after we have 4 elements. The way you will implement take is actually very similar to enumerate, because you also have a count. There is one difference, of course, which is that you start, and here you can see another example of how you use the parameters inside the initial state. The initial state is the count. And then, from the count, you go down. You take 1 every step. Now, you will say, well, this can wrap around 0. This is going to be not so nice, actually. But there is something new here, which is when we grab the state, we pass a tag. This is the tag that we saw for the state grabber. The tag is the take tag. This allows us to define one operation for take. And this operation is called state grabber data is reduced. And basically what it says is my transducer, given its current data, its current private data, is it done? And in this case, it's done when the count reaches 0, right? This is the tag that we gave. Now, we need to do one last change then to reduce as well. We need to say, is it reduced already, right? Inside the loop. Now, I'm giving all these examples of how you execute the step functions with reduce. Again, reduce is an example of a sequential process. if you were transducing boost signals, you will have to kind of translate this structure here to the structure of boost signals. There are actually batteries included in the library to do more things. Another example is reduce nested. So we saw there is reduce, but reduce calls complete inside of it. Maybe you want to reduce inside a transducer. One example will be cat. The example with Charlie Chaplin getting the things from the array. Cat, what it does is it takes arrays or vectors, collections, and then passes on the individual elements of the collection. It flattens, right, or concatenates, hence the name. The way to do this, it's simply, it gets the inputs. The inputs are is a collection. It says, well, what I'm going to do is to reduce the collection with the next step function. So every element in this collection is going to be passed to the step function individually. Now, the state grabbers are important here. So this one needs to return the state grabbers because they contain information like, am I done? So to preserve them, that is reduce nested. Another utility is reductor. And reductor will be something that actually you could use if you wanted to implement your boost signal adapter for transducers. What it does is to provide a more object-oriented interface to perform a reduction, taking into account all this is reduced, the change in type during the first iteration and whatnot. So it's parameterized over a reducing function, a state and some inputs. And what it provides is operator parenthesis, so it's a function basically, but it doesn't take a state. The state is encapsulated into the object. That's why it's an object-oriented way of doing this. And it just takes the inputs. Then it provides a conversion to bool, an explicit conversion to bool to be safe. Actually, I should remove without the inputs here. That's a typo. That basically is reduced. Am I done? But negated. So you can do while my reductor says true, I continue, otherwise I stop. And then provides current, which returns the innermost state without the grabbers at the current moment without completion, and complete, which completes the state and returns it. So you can imagine how this could be useful. For example, if you wanted to use the boost signal, actually, you could directly create one of these objects and pass it to the boost signal and so on. There is another thing that is provided in the library, which is transducer, which is basically std function for transducers. As you have seen, the transducers are lambdas written for lambdas from lambdas from lambdas. They have anonymous types, very complicated types. Even if you implement them with templates, template structs, they're going to have complicated types because they compose and their types grow and grow. So if you wanted to do type erasure, the transducer thing allows you to express only the inputs as first argument, as first parameters, and the outputs as second parameter. This pack here is just a type list. So this thing actually that takes integers and can produce pairs of integers can be stored in this thing without expressing the full type. It has the problem that it's actually expensive. It's more expensive than you will expect for an std function because of the type erasure of the state variable. But in some cases, it might be what you need. It might be the right solution for your problem. Normally, I would recommend to try to do the type erasure at a different level in your system if you can. There are lots of transducers implemented in the library. There is all of the transducers from the Clojure standard library are also provided in our implementation. There are some of what's provided in Python's iter-tools re-implemented or reconceptualized as transducers, which can be useful, especially when dealing with collections. And some transducers of our own that were not in any of these libraries as transducers. The final thing to talk about is performance. And to talk about performance, I'm going to talk about move semantics for only one time, which is here. And with this change, what we are doing is to move the state on every iteration. Oh, sorry. So to come back, the problem with this loop here is that basically on every step, we're copying the state, right? We need to copy the state into this function, and then it's going to return the next state. If the current state is, for example, a vector, because we are accumulating everything into a new vector or something, this can be expensive. And we want to support actually having expensive state here, because we want to be functional. We want to have all our state in this variable. So the way to solve it is to move it. But we cannot move it directly. We have to move it in 2 steps. And this is because the standard says that the move assignment operator can assume no aliasing. This means that basically the left-hand side cannot be the right-hand side. Now, the step function, if it's an identity function, could be returning us the same thing as a R-value reference that we pass to it. And this will break the rules. So the way we do this is this 2-step. We create a new variable where we move into, and then we move this variable into the state. This solves the problem, and it's optimized away in most cases if you're doing simple operations anyways. Now with this change, the transducers are fast, and that's the good thing about performance with transducers, because if you use forwarding of your inputs, of your states and everything, it's a chain where every function doesn't need to copy anything, right? Everything goes to the next one, and then it's returned from the next one, and there is no copy in between. So that's good. They're also small functions, so they're easy to inline. And my experiments show that Clang and GCC, they have no much trouble inlining these kind of functions. Of course, if you make a complicated transducer, then it's going to be hard to inline. But many of them, especially of the most common ones like map and filter, they're really easy to inline. In fact, they're so easy to inline that the simple cases like composing a map with a filter and passing it to an accumulate to compute a sum, it's going to be as performant when using transducer than if you write the for loop by hand. So this is quite good. They are actually even faster sometimes than equivalent boost range adapters, because the boost range adapters are not so easy to inline because they have a reference to the next iterator there and so forth. The ugly part is that type erasure is expensive for transducers, as we discussed for this transduce thing. Filtering before a stateful transducer also adds overhead because of this union type that it needs to return. There are alternative designs that I would like to explore actually that don't require this union type. I still will need to try them and measure. You can also use a stateful transducer instead with mutable state if you really need that performance. And adapting as an iterator, this sequence thing that we saw, has a small overhead as well if you compare it to equivalent boost range adapters. And that's because this thing needs to keep a queue. A transducer can produce more inputs than it takes. So the only way you can adapt this into a pool model is to queuing up all the inputs that you're getting. So finally, conclusion, very fast. If I want you to remember something about this talk, is that a transducer is a transformation, that is a value, that is composable, and that is independent of the process, of the sequential process that it's transforming. We have an implementation in C++ that is pure. This is a surprising result, actually, that in C++ we could make a pure implementation, where in Clojure, actually they could, but it will be very expensive. So you would never think about a case where C++ can be more functional than Clojure. Well, this one. It's fast as well, so it's a very lightweight abstraction. You can use it in performant code. It's a work in progress, so some of the interfaces are bound to change. I would really like to hear actually your critique and what your thoughts are about this. And since we are in a C++ conference with a lot of people that are in the standards committee, I wanted to include this question because I think this is a very general construction, I think, that complements very well all this new work in in introducing ranges and views. So I would like to think, could this be somehow eventually material for a proposal for the standard? In the meantime, you can download our implementation in our GitHub page, and thank you very much for listening. Yes?
Yeah, so you said in the original, the actual implementation, the state is movable. So can it be also not copyable, but just movable, right?
Yes.
And what about the functors? They're always copied, the functions, or they can be also moved?
Yeah, our functions, actually, we take them by universal reference, and so we don't copy them. They are also moved, yeah. But, I mean, you could think of, wait, sorry, no, they're not always moved. No, yes, okay. So when the transducer takes another one, if you pass another value reference, it's gonna be moved inside the wrapper, yes. The other one over there, I think, oh, we need to finish. Yeah, we're done. Okay, well, thank you very much.